Good morning students. Today we are moving to P block elements. Under P block elements we are going to see group 15, group 16 and group 17, 18. So these are the four groups which we are going to see under P block elements. So we are going to see P block elements. Under P block elements we have from group 15 to group 18 elements. We are going to see all that. Yeah, moving to the first slide. This is an overall, this is just for your memory, like where group 1 and 2, which is nothing but S block elements, this is P block elements. In between you have D block elements, representative elements, that is group 1 and 2 along with group 13 to 18 elements are collectively called as representative elements. Here is group 18 and down you have S block elements. So S, P, D, F, it's an overview. Next slide is also about the overview only. See here 1 and 2 P block, group 3 to group 12 D block, group 13 to group 18 is P block, group 13 to group 18 is P block elements, and down you have F block elements. This is an overview slide. Next, moving to the introduction of P block elements. See, I have already told you P block elements means the elements which are belonging to group 13 to 18 are collectively called as P block elements. What is their general electronic configuration? It is NS2 NP 1 to 6. What is the electronic configuration? NS2 NP 1 to 6 is the general electronic configuration. So as I told you, group 15 to group 18 will be included under this category. Next, now look into the group 13 to group 18 elements. Next you have your noble gases. The main reason for this is we already knew how to remember them. Say for example group 18 is your inert gases or noble gases. How to remember them? Hina, Nina or Karina ka X-ray rangeen. Okay, helium, neon or krypton, xenon, radon. Hina, Nina or Karina ka X-ray rangeen. And see this one also I can help you. Bengan, aloo, gajar in thaila. Okay, bengan, aloo, gajar in thaila. This one is see carbon, silicon, germanium, then tin, lead. This one I can help you, I think. Na pina aise sabke beach. Na pina aise sabke beach. Na pina aise sabke beach. I have a few hint also. In the live session I will be helping you how to remember these three very easily. Okay children, yeah, this is an overview. Yeah, the main aspect of this slide is I want to differentiate metals, non-metals and metalloids. You know, group 14 will be your metals and group 17 will be your metalloids, which show both the properties, and this will be your non-metals because they are inert gases or noble gases. So about the general introduction, I have told you group 13, group 15 to group 18. We know what is the general electronic configuration. It is NS2 NP 1 to 6. Okay. Now coming to nitrogen family, I am going to call them as nitrogen family. Nitrogen, phosphorus, arsenic, antimony, bismuth. Now see nitrogen, phosphorus, arsenic, antimony, bismuth. I told you no, na pine aise sabke beach. Okay, now nitrogen, phosphorus, arsenic, antimony, bismuth. So these 5 elements will be coming under group 15. Okay. Now what are the possible existence of nitrogen? Nitrogen can exist in the form of dinitrogen, that is dinitrogen N2, then nitrous acid, then ammonia, and oxo acids of nitrogen. Oxo acids of nitrogen is not included for final exam. And phosphorus is also not included for final exam, but just I am giving you an outline. Phosphorus, trichloride, pentachloride, phosphine and oxo acids of phosphorus. So these all we will be covering under group 15 elements. Now this is the element. What is the symbol of nitrogen? N, phosphorus P, arsenic AS, antimony SB, bismuth is Bi. This is their atomic number and this is its electronic configuration. And this is its occurrence in parts per million in the earth crust. You know which is the most abundant thing? It is the element is phosphorus, and the one which is very least is said to be bismuth. Yeah. Then this is the trend. This is there in the syllabus, like what trend your nitrogen family is going to follow. What happens to the ionization energy? What happens to the atomic radii? As we move down the group, what happens to each of the definitions we are going to see now. very detailed and it's a very compact definition. Just remember the flowchart, easily one topic is cleared. Now the first topic is electronegativity. Okay, I am possessing a negative charge, means I will be attracting. Okay, I am more electronegative, so I have the ability to attract electrons. I have the ability to attract electrons. So what happens to this electronegativity? It decreases as I move down the group. When I move down the group, it decreases. Now what is ionization enthalpy? Amount of energy required to remove an electron from an atom in the gaseous state. Okay, now this also decreases. So electronegativity decreases, ionization enthalpy decreases as we move down the group. Now what is the third definition? It is atomic radii. What is atomic radii? Radius of the entire atom that increases because the size of the atom increases. Now electron affinity, ability of an atom to accept an electron. You can say your electronegativity and electron affinity are one and the same. Electronegativity, it is attracting the electrons, and electron affinity, it can accept an electron. So electron affinity also decreases. Electron affinity also decreases. What happens to melting point? You know what is melting point? Amount of energy required to convert any substance from its solid state to liquid state, and melting point increases when we move down the group. And what happens to the boiling point? Energy required to convert a liquid to a gaseous state. Your boiling point increases as we go down the group. So in all the trends which we saw, electronegativity, ionization enthalpy, atomic radii increases, electron affinity decreases. So three aspects of electronegativity decreases, ionization enthalpy decreases, and electron affinity decreases. But size of the atom, it increases as we move down the group, and melting point and boiling point too increases as we move down the group. So this is nothing but a trend in the periodic table. Now what are the possible allotropes? Okay, what are the possible allotropes existing in more than one form? Nitrogen can exist in the form of cubic crystal. It also exists in the form of a crystalline form, hexagonal crystalline form. Okay. Now what happens to phosphorus? Phosphorus occurs in three forms: white phosphorus, red phosphorus, and black phosphorus. Now moving to arsenic. Arsenic appears as yellow arsenic, black arsenic, and grey metallic arsenic. Okay, these are the three allotropic forms of arsenic. Coming to antimony, it exists in yellow form, it exists in metallic form, it exists as explosive. For bismuth, there is no allotrope because already it exists in very, very low concentration. So there is no allotropic forms for bismuth. Now moving to the chemical properties. This is all we have seen in our lower classes. So by seeing the reaction only, you should tell me the product. So first reaction is action with air at a high temperature. Action with air at very high temperature. When nitrogen reacts with oxygen, I will be getting nitric oxide. Done. Now when phosphorus reacts with the nitric acid, I will be getting orthophosphoric acid. What is the product form? It is orthophosphoric acid. See children, I will give you a small hint. In the reaction of phosphorus, arsenic, then antimony and bismuth, all these reactions are with oxidizing agent. The oxidizing agent which we have taken is nitric acid, HNO3, nitrous acid. Now in all these cases, apart from one end product, the compulsory two end product will be NO2 and water. The compulsory other two end products will be what? NO2 and water. See, can you see this? NO2 and water molecule. So this is orthophosphoric acid, this is arsenic oxide, this is antimony oxide, and this is bismuth nitrate. This is bismuth nitrate. Clear children? So these are the chemical reactions. Then moving to the action with, now we have seen with nitrous acid, right? The reaction all we have seen is with oxygen as well as with nitric acid. Now next reaction is with the sulfuric acid. How I told you a small hint for nitric acid, the compulsory end product should be NO2 and water. Similarly, when you add sulfuric acid, you can close your eyes and say SO2 and water will be the end product. Okay, SO2 and water will be the compulsory end products. Now consider the reaction. When phosphorus reacts with the sulfuric acid, I got orthophosphoric acid plus sulfur dioxide plus water molecule. Now when arsenic reacts with sulfuric acid, we got arsenic hydrogen oxide. Now consider antimony with sulfuric acid, antimony sulfate plus sulfur dioxide plus water. Now bismuth plus sulfuric acid gives bismuth sulfate. Now we have seen acids. Okay. We have seen oxygen, we have seen oxidizing agents. Under oxidizing agents, we saw nitric acid and we saw sulfuric acid. Next, moving to the action of alkali. Alkali will be NaOH, KOH, etc. So when phosphorus reacts with NaOH and water, I'll be getting hydrides. I'll be getting sodium hydride, sodium hydrogen phosphate. Now what happens to the action of metals? When my nitrogen reacts with magnesium, I'll be getting magnesium nitrate. When phosphorus reacts with magnesium, I'll be getting magnesium phosphide. So these are the products with metals. Yeah. Among the action of oxidizing agents, the important reaction will be the formation of hydrides. So what is the general formula of group 15? I mean our nitrogen family elements, their general formula will be EH3. That is, when they react with the hydrogen, their general formula will be EH3. What is E, children? E can be nitrogen, phosphorus, antimony, bismuth, etc. Trihydrate. So what you are getting? Trihydrates. When nitrogen reacts with the 3 hydrogen, you will be getting ammonia. Yes, no? So antimony trihydrate, bismuth trihydrate, like that we will be getting trihydrates. Now look into the stability of the hydrides. The stability of the hydrides will be decreasing. Why stability decreases? Because bond dissociation energy decreases. Okay, children, the stability of these hydrides decreases as I am moving down the group. Why? Because the bond dissociation energy is decreasing as I am moving down the group. Okay, children, this is the structure of ammonia. This is how I am going to compare the hydrides, and I am going to tell you the reason for that. Now look into the first property. What is the basic strength of MH3? You replace M in terms of nitrogen, phosphorus, antimony, bismuth. Now what happens? The basic strength of MH3 decreases. Why decreases strength and strength? Why strength is decreasing? Because the size of the central atom increases, because of electron density decreases. I am clear? I am repeating, the strength of all hydrides decreases. Why it decreases? Because atomic size increases and electron density decreases. Done. Now moving to the second property, what happens to the thermal stability? When you heat it, what happens to their thermal stability? Thermal stability also decreases. Why? Because your central atom size increases. As a result, the tendency to form stable bonds between my nitrogen to hydrogen, that is M to H, that stability is also decreases. Okay, what is the second property? Thermal stability also decreases. In both these cases, the size of the central atom increases. That's the reason why the trend decreases. Now moving to the reducing character, the reducing character increases in the trend. Why the reducing character increases? Because stability of the hydride is decreasing as the reducing character increases. Okay, children, we saw in these two aspects the stability decreases. Stability of hydride decreases. Since the stability of the hydride decreases, the reducing character obviously increases. Moving to the last property, melting point and boiling point. We know that melting point and boiling point increases. You know why it is increasing, but it increases in the same trend like nitrogen, phosphorus, arsenic, antimony, bismuth, except in case of nitrogen. Why? Because ammonia has high melting point and boiling point than phosphorus because of hydrogen bonding. Ammonia has high melting point and boiling point. You know, NH3 is having high boiling and high melting point compared to PH3, phosphorus trihydride, because of hydrogen bonding. As the molecular size increases, the van der Waals forces increases. This is the reason why our melting and boiling point increases. So melting and boiling point increases except in case of nitrogen, there is a gradation. Why? The melting and boiling point of nitrogen is more than pH3, after which the trend is quite different. Why? Because of extensive hydrogen bonding. Because molecular size increases, the van der Waals force also increases. So these are the four properties which we have seen. What are the four properties? The first property will be basic strength, then thermal stability, then reducing character, then melting and boiling point. Like how in 11th standard, among all the family elements, we have one exceptional extraordinary ferro. Similarly, in nitrogen family, nitrogen itself is exceptional. Why? The first point, you know, it's a gas while all others are solids. Okay, nitrogen is a gas while all others are solids. and it is diatomic. It exists in the form of N2, but all others are tetraatomic. And you know, it forms hydrogen bonds and hydrates. Like, what is nitrogen trihydrate called? It is ammonia. So it obviously forms hydrates. Then it forms p pi pi bonds. It forms p pi pi multiple bonds, and its oxidation state ranges from -3 to +5. Okay, it exists between -3 and +5. And you know, there is no d orbitals in nitrogen, so it will not form any coordination compounds. Done. So these are the exceptional properties of our nitrogen. Coming to dinitrogen, how to prepare dinitrogen commercially by means of fractional distillation of air, as well as you can, this is one way, that is fractional distillation. Hope you all remember about the use of a fractionating column and a different boiling point, what happens. So it can be prepared by fractional distillation of air. This part we have seen in class 9. Okay. Now apart from this, you can also produce them by means of lab method. How to prepare dinitrogen in the laboratory? You should take ammonium chloride. What is the formula for ammonium chloride? NH4Cl. And add sodium nitrate. So sodium chloride and water is removed. Nitrogen, dinitrogen is prepared. Then from acid, sodium acid. What is the we have seen this. What is the formula for sodium acid? NaN3. NaN3. From sodium acid, I got sodium and dinitrogen. So two methods I have told you to prepare nitrogen, that is dinitrogen, in the laboratory. One is using ammonium chloride and sodium nitrate. Okay. Second way is from sodium acid. Then what is the chemical property? We know dinitrogen exists in the form of two isotopes. One is N14 and other one is N15. These are the two possible isotopes. Now moving to the chemical property, this you can tell me. When magnesium reacts with the nitrogen, you will be getting magnesium nitride. Then when hydrogen reacts with the nitrogen at high temperature, we will be getting nitrogen trihydrate, which is nothing but your ammonia. Then when nitrogen reacts with oxygen in 2000 degree Kelvin, what is the product form? Nitrogen oxide or nitric oxide. Then calcium carbide along with the nitrogen, you will be getting calcium cyanamide. What is the product here? Calcium cyanamide plus carbon. Okay, so we have seen dinitrogen's preparation. What is its chemical reactions? Then moving to preparation of ammonia. Whenever I told preparation of ammonia, then immediately you should remember Haber's process. Okay, that's a commercial method to produce ammonia. So the first lab method is heating ammonium chloride and calcium hydroxide. And how to prepare ammonia in laboratory method? How do you prepare dinitrogen? Hope you all remember ammonium chloride plus sodium nitrate. Here using ammonium chloride and calcium hydroxide, I got calcium chloride, then ammonia plus water. Okay, my intention is to produce ammonia because we are seeing the preparation of ammonia. So ammonium chloride is the same starter for the preparation of ammonia too. So I have taken ammonium chloride and I have taken calcium hydroxide. So what is removed? Calcium chloride is removed and ammonia is produced as the end product. Now this ammonia produced, this can be collected in the upward because it is very lighter than air, so it is dried over quickly. Ammonia is collected in the top. Since it is lighter than air, you can dry them on the calcium oxide, which is nothing but your quicklime. Now this is the manufacturing of ammonia in the large scale. This is nothing but your Haber's process, which we have seen in many sessions. Ammonia which is collected in the condenser, and this is your liquid ammonia. See, nitrogen and hydrogen compressed, and unreacted gases will be moved into the condenser and it will be collected as liquid ammonia. In the chamber I have nitrogen and hydrogen. I have given 200 to 900 atmospheric pressure, 450 to 500 degrees Celsius. The catalyst will be iron and molybdenum. I will be getting ammonia as the end product. This ammonia will be collected in the form of liquid. It is condensed. Yeah, whatever the flow chart which I have shown you, this is nothing but an explanation for this. What is Haber's process? You have to treat nitrogen and hydrogen in the presence of finely divided catalyst. Now what is this catalyst, children? I told you I am going to react nitrogen and hydrogen in the presence of finely divided catalyst. What is the temperature? It is 700 degree. And what is the required atmospheric pressure? It is 200 atmospheric pressure. Now, I told you finely divided catalyst should be added. What is that catalyst? It is nothing but your ferric oxide and potassium oxide that is added as a catalyst so that the performance will be improved further. Now, the reason for adding aluminium oxide, ferric oxide and potassium oxide is they make porous, so high surface area will be provided for the reaction. And the reaction is reversible, so all the substrate will not be converted into product. Since the reaction is reversible, it's not possible to convert all the reactant into ammonia. Now, how to separate ammonia from the mixture? You need to cool the mixture first. Only ammonia will be liquefied and it will be separated. Then there are some uncombined nitrogen, that is unreacted nitrogen and hydrogen present. They can be recycled for the further reaction. And another way of separation is you can pass this mixture into water, only ammonia will be liquefied. So that's also a method. So this is an overview of Haber's process which we have seen in the flowchart. And you know this is the structure of ammonia. Ammonia has a lone pair, and you know the bond angle is 101.7 picometer.